Chien-Chang, but everybody is calling him Simon. I'm beginning to think that's like his just real name.
Hi, I'm Simon. So today's my talk will be very easy. And today I want to tell you a story about NEP, Subaru, Akari, and Photometric. So once upon a time, there was a man, he has Subaru HSC data. He also has Akari data. So one day he merged.
Can we see that again?
He doesn't want to.
So the NEP catalog I'm talking about is merged by Songjin Kim and still updating. And the catalog I use for running Photometric is the most updated one. So sources in total is around 74,000, and sources with specs is around 2,000. So the code I use is called Rufa, and Rufa in French means lighthouse. So it is SCD fitting code which can run Photometric. So in total I use 25 bands for running Photometric. You may ask me, Simon, 25 bands, isn't it too much? Isn't it too many? So here I show you different bands filtered with different effective wavelength. You can see that even they are called either Nike R, Subaru R, or even CMH R, they have slightly different effective wavelength. So in order to make the best performance in SCD fitting or Photometric, you need to have as many as possible bands, filters to get the best results. Also, we can see this SCD. So you can see that there are many features in the SCD for different redshift. For example, for low redshift, there are Lyman break, so we need infrared data. And for high redshift, there is Lyman break, so we need optical data, maybe U-band data. Therefore, I chose 25 bands from either Nike to WISE. So before running the code, before running the Photometric code, I need to design some context for the special cases in the catalog. So the first problem I found in the, not problems, the first special cases I found in the catalog is there. You can look at this right SCD. You can see that the green cross and the blue cross. They are the Nike data and Subaru data. They are a little bit correlated. They are in a different of like 2 magnitude. So Nagisa-san helped me to look at this source. So we can see that from the HSC image, this is actually a very large bright source, and the HSC detection is many. So the catalog is in fact using one of this detection, and this detection is in fact fainter than the actual flux. This makes this difference. So I plot something like this. This is HSC R minus Nike R versus HSC R. So I try to use 3 sigma principle. I use context for sources which is larger than smaller than plus or minus 3 sigma, which are circled with the blue circle. So I use context for them. The next problem I found is that there are some bad photometry in Flamingo J data. So we can see that in the red circle, for Flamingo J data, sometimes it pop out from SCD. Therefore, I again use 3 sigma principle. I use context for HSC Y minus Flamingo J versus HSC Y. I use context for those 3 sigma outliers. So they are circled with the blue one. So before I show you some Photometric result, I want to show you some definition. So this figure here is a total C versus spec C figure I have. And you can see some symbol right here. So I want to talk about this. So the first one I want to talk about is sigma, and I call it Photometric deviation. It's actually the normalized median absolute deviation, and it is defined by this formula. And the next one is eta. It's an outlier fraction, and outliers here are divided by delta C divided by 1 plus spec C, which is larger than or smaller than minus 0.15. And it is shown in the blue dashed line. And the next one is N-gal, is number of included galaxies in each photo C1. And the final one is back CU of the photo C is presented by the red line. Basically, for sigma and eta, the smaller the better the results. So, because photo C is actually a regression problem, you need to compare different kinds of setup and parameters to have the best results. So, the first thing I want to compare is the filter combination. And the control variable here is the cosmos, the galaxy template. Here I show you different parameters, different filter combination. So you can see that the blue bar is the outlier fraction and the green bar is the redshift deviation. We can see that for setup A, it has the best results based on its eta and sigma. And actually setup A is 25 bands, which I just mentioned from Meta-Knight to Weiss. And the next thing I want to compare is the template models. So this time I control the 25 bands as a control variable. So here I show 6 of the template model from Cosmos to CWW. So we can see that Cosmos actually performed the best. It has the outlier fraction which is 25.5% and redshift deviation which is 0.079. Therefore I claim that for our catalog, the NEP catalog, the best setup is SCD template which is Cosmos and filter combination is 25 bands filter from Meta-Knight to Weiss. And the performance is eta is 25.5% and sigma is 0.079. For the redshift, which is from 0 to 1.5, the result is like this. So around 300 data are excluded, but now the outlier fraction and sigma are much better. So it has a 50.9% outlier fraction and 0.06 in the redshift deviation. And I think it's good enough for maybe scientific research. And I did a little bit more analysis. So the first analysis is on the chi-square value of my photo C results. So here I show different color is the different chi-square value. So the blue one is smaller than 2,500 and 2,500 to 5,000 is the orange one. And the green one is 5,000 to 7,500. So on. And I try to exclude those. So you can see that the outlier fraction is worse when the chi-square value is larger than 7,500, and the redshift deviation is really bad for more than 7,500. So I try to exclude them. So this is the result after removing chi-square value which is larger than 7,500. We can see that around 500 data are excluded. However, the result is similar. The sigma now becomes 0.06, so it's only 0.002 better, and the eta is only 2% better than the original one. Therefore, I decide to keep this 500 data instead of removing the bad chi-square value. So the next thing I do is do an analysis on the magnitude. So here I show different color is different magnitude in my photo C results. And here I show 5 different magnitudes. So this is HACI, which is smaller than 21, and 21 to 22, 22 to 23, 23 to 24, 20 larger than 24. We can see that for HACI, which is larger than 24, there are many outliers, which is around here. So therefore, I decide to try excluding those HACI, which is larger than 22. So this is the results. I exclude around 270 sources. However, the result is not better. Actually, it's worse for the data. So again, I try to keep these 200 data rather than removing them. So I can claim that for redshift 0 to 1.5, only setting this redshift range is good enough for my data. And this is probably the best I can do now for the photo C results. However, is this good enough? So I find something like this. This is actually the machine learning in Photo C. So I found a code from this textbook, and the AI type is random forest. So I try to use machine learning for doing Photo C or NEP catalog. So how it works? In total, I have 2,000 data. So I try to use around 1,900 as the training set and around 200 for the test set. And the input data are the 25 bands photometry and the spec C. And guess what? So this is the results from machine learning Photo C. It has the results for 199 test set samples. It has a result of 12% outliers. It's better than the original one. However, the outlier, the Photo C deviation is similar. So I can claim that for the NEP cases, the AI weight and SCD weight is roughly the same. However, you may have a question, is machine still let SCD as strong as job? So actually I think about it. So there are actually good things and bad things about AI Photo C. So for advantages, it's really fast. It only took me like 5 seconds for running the code. But and also it's very simple. You only need to control 3 parameters, like the tree depth. For random forest is tree depth and test sets numbers, training set sample, and then you run the code and then take 5 seconds. However, there are some disadvantages. For example, the result is strongly biased to the training set. For the NEP catalog case, my training set is the spec C data, so they are very bright, so it may be biased, and you cannot obtain Photo C for the training set. Moreover, you cannot check the SCD. So this is summary for my presentation. Thank you.
Interesting. All right. Questions on this? Kenneth. First dance.
Do you have data in all the bands for all the objects?
All the bands.
Yeah, I mean, for each band, do you have data for every single object? Or do you have faults? Sometimes if you don't have the V band or so.
No.
Because when you compute the chi-square, just the chi-square is just a reduced chi-square, right?
Yes, yes.
So if you don't have the same number of bands for each object, you might have difficulties to compare different chi-square.
Yes.
So when you cut to, I don't remember which number, maybe the cut is not exactly what you want to do. See what I mean? No? Okay, we can discuss it.
Okay.
Yes.
Have you ever compared the result between different models? I mean, you have done the model between, you have done a comparison from model photo Z between the spectral Z. But have you ever compared the photo Z between photo Z from different models? I mean, if there are some objects, their photo Z result is consistent in all the models, maybe they are more accurate.
I can do it in the future.
Okay.
Yeah, there's a question back.
Can you go back to the slide you showed the final result of the Cosmos template? No. I just wonder why even in the safety zone, the result is looks like it's artificial, right?
We talked about that a lot.
Sorry. You are talking about this kind of zigzag feature. So for the vertical one, it's probably the cluster. But for the horizontal one, I'm still thinking, what is that? It might be come from the what is that? The photometry of the data.
Yeah, I think it's the band passes that you have.
Yeah.
Okay, so we don't know what it is. So if you have any idea,
Yeah, I mean, it's obviously fake, but
Yes.
we don't know how to fix. You don't know how to fix.
Yes.
I think you said you were using the far to
Yep.
Yes.
run this. Have you tried the easy?
Not yet. Maybe I can try.
I guess, well, it's, they have pros and
Pros and
cons.
cons.
Yes.
But it's worth a try.
It's very easy to run. And the nice thing about easy is that if you have some uncertainties in your zero points, for example, you can compare, for the good fits, you can compare the predicted model photometry to the best fitting model to the actual photometry. And then sometimes you will immediately see that one band is off
That's right.
from what you
Yeah.
expected, and then you can
Fix it.
adjust it and you can rerun your, and then in that way iteratively improve your photo sheets.
Thank you.
Toshi.
Do you have any explanation why Cosmos template is best?
My guess is that for Cosmo template, it covers the largest amount of galaxy template. It's covered like 31 galaxy template. It's more than other template model. So I guess this is the reason.
Yeah, well, you have more infrared data than typical studies, maybe, except Cosmos. Yes.
Are you sure that you found best model in your machine learning, or can you find improved model?
By adding the
More better.
yeah, this is possible. Actually, I try to add AGN because Cosmo doesn't have AGN template in this model, so I try to add AGN, but it works not better. Maybe I can try more different kind of template model in the future. Thank you.
My guess is that when you looked at a lot of these, I mean, sometimes the reason you can't decide exactly what the redshift is, as you said, you look at the photometry and it doesn't quite match. It's just not a smooth curve. So what are you going to believe? These photometry points or these points? Doesn't matter what model you have. Just the data just isn't quite clear. This is my impression. So we're going to take a coffee?
Yes, sir. So now is the time for coffee break. Thank you, Simon. So we only have 7 minutes to have coffee.